Okay, so in this lesson, we're going to go over some of the basic graphs that we use in statistics, and these are going to be for quantitative data. So we're going to look at how we make dot plots, stem plots, and histograms. And then we're also going to look at how we compare sets of data and just knowing specifically what attributes to focus on. So the beginning of this lesson is actually going to be pretty simple. It's probably stuff you've seen and done even in middle school. But one of the simplest graphs that we use to graph data is a dot plot. And simply what you would think, it's a set of dots that show how many of each value are taken up in a distribution. And I'm going to go over a couple of examples in a bit. So just hang on. Now, let's understand that when we're in statistics, your goal in the course is not really to be able to show you can make dot plots or calculate, averages. It's really to be able to analyze data and decide what you need to do. So keep that in mind as you're working through problems and, just going over your notes and stuff. Now, when we're examining distributions dealing with quantitative data, so remember quantitative data are values such as the heights of people, the weights, stuff like that. You want to look for the overall pattern and for anything that doesn't really go with that pattern, so any departures. And we need to focus on addressing the shape, the center, the spread, and make sure we mention or talk about any outliers. So remember, an outlier is something that doesn't go with our overall pattern. It could be actually very, very far below or far above the values in a set of data. When you think of the word outlier, think of the word outcast. Kind of helps get a easy way to remember that. Now, a good way to remember what you need to address when you're describing set of data is to use the acronym SOCS. So S-O-C-S, not S-O-C-K-S, but S-O-C-S. This will let you remember that the first S stands for shape. The O stands for outliers. The C stands for the center. And then the other S will be the spread. This is especially important, especially if you're going to be taking the AP Stats exam, because you're going to be given problems that aren't going to prompt you with what you need to determine when you're dealing with a set of data. It's not going to say describe the shape, figure out there are any outliers, identify the center. It's not going to say that. It's just going to say compare the data or talk about the data. So you're going to need to know that you need to address these. So keep that in mind on let's say AP free response questions. Well, and what's actually good about these types of problems is they're actually pretty easy as long as you remember this, because they're pretty much common sense. It's not like you have to know some advanced, complex way to describe a set of data. So let's go over an example. So let's say we want to make a stem plot or a dot plot actually of the number of pairs of shoes that classmates in your stats class have. And then we're going to describe it. Now I'm just going to use the example that I did with my class from a previous year. So we can switch over and I'll just talk about it. It's pretty, this is a pretty simple graph. So these are the values that my students gave me. And for a dot plot, you just make a scale that includes these values, and make sure you don't skip them. Make sure you don't skip anything. Make sure you go with 0, 1, 2, 3, 4. Make sure you include everything from 0 through 15. Don't skip 13 and 14 just because there aren't any values. That's a big deal. And all you do is put a dot over however many of those values you have. So I had 2 5s, I had a 1 6, 4 7s, and so forth. Now, when we describe this data, again, just make sure you address the shape, center, any outliers, and spread. So the shape, you can say it's kind of skewed to the right. It's not really perfectly symmetric or uniform. Outliers, you could say there's a possible outlier of 15. And for now, we're going to say possible because we haven't learned a numerical way to like actually determine if something qualifies as an outlier. So right now we're just kind of going over the basic idea. And the center, again, we would say around 7. And again, we haven't learned the precise or calculated way to determine what the center is. We just look at like what the middle value is. And then the spread, we just say that the values can go from 5 to 15. So that's a very general example when we're describing a set of data. Now, let's talk a little bit more about when we're discussing the shape of a distribution. When you discuss the shape of a distribution, you're gonna look over the main features and don't really, focus on little, tiny ups or downs. Look at the big peaks. Again, look at the overall picture. Look for, groups or clusters of values, and for, gaps, gaps where there aren't any values at all. So if I went back to here, I could say there's a gap between 12 and 15 because there's no values at 13 and 14. Potential outliers, again, values that don't really go with the pattern. So like an outlier would be over here. And if I was to maybe be a little more specific, I could say there's a cluster that's down to 7 or 8 because there's like 6 values right there. And try to address any symmetry that you may see or any clear skewness. Now, there's never going to be a graph in real life that's perfectly symmetrical. It's pretty much impossible. So that's why we say rough symmetry or approximately like symmetric. Okay, so now let's talk a little bit about what it means for a distribution to be skewed in the left and right direction. So symmetric is if you would like, it was what you would think like a graph would look like. But the left and right sides of the graph are pretty much the same looking. You could say something like a graph like this would be, that's a common bell curve. That's symmetric because the portion to the right is about the same shape as the portion to the left of that line. Now, if we're saying skew to the right, we're saying that the tail of the graph tends to veer off to the right. This would be a skewed right. If you're talking about skewed left, then it's the other way around. The tail veers off to the left. Now, when we compare distributions, we simply just look at those characteristics and compare them piece by piece. And this is really what we're going to be doing a lot in the course, because we really are going to be asking questions that involve 2 or more groups. That's really what real life is about. There's no such thing as tall people unless there's short people. There's no such thing as smart people unless there's not smart people, I guess, or fast people unless there's slow people. So we have to compare groups in order to really talk about and use statistics. Okay, so let's look at this example. And this is real data, by the way. It may not be so interesting when you're a teenager, but when you get older, you care a lot about how much money you spend on your electric bill. So here's 2 dot plots that show the energy cost for these refrigerators at bottom freezers and top freezers. So here, shows the average energy cost in dollars. And so let's compare them. Now, again, when you're going to be, going through these problems, I would focus just looking at each thing, each characteristic, shape, center, spread, any outliers one at a time. Because then you'll be more organized and you can go about it more systematically, especially when you get these types of problems on an AP exam. So the shape, we could see that this top, or in this case, the bottom freezer graph looks more skewed to the right. It looks like it's going like way out there. Whereas the top freezer distribution looks more symmetric. We have some, peaks over here around like $58 and $70. And then looks like the top freezer one has the center around $55. So address, things that stand out, but the best way I would say is just use common sense. Don't try to be like very like statistical. Don't try to be like you have to say it in a very complicated or fancy mathematical way. All right, center. So again, I would say the center is probably around here for the bottom freezers and around here for the top freezers. So to calculate that value, it's right at 69 I found. And for the top freezers, about $56. But again, just an estimate for now. If you say you're 70 or 68 or 55, 59, 58, you're fine. It's not going to be a big deal. We just want to get the general idea down for now. All right, the spread. So you're just basically saying, the bottom freezers have much more variability than the top ones, the values go all the way from looks like 50, I think it's like below $50 all the way to above 150, while a top freezer only goes from, I think that's $48 to right below 70. And outliers, there seems to be 2 outliers for the bottom freezers over here. And there doesn't really seem to be any obvious outliers for the top freezers. All right, next we're going to look at stem plots. So stem plots, you probably also heard of them being called stem and leaf plots. You probably, worked with these in, some part of a middle school class even, but it's probably been a while, so we're going to go over an example. Okay, so here's some data on the heights from one of my classes from a previous year. And this is their height rounded to the nearest centimeter. So I put them in 2 groups, the females and the male heights. So we're going to make a stem plot, including both sets of data, or both groups. And then we're going to make a back-to-back stem plots where we break it into males and the females. So for a stem plot, you start off by, making your stem, and you do that just by drawing a vertical line. Now, on one side of the stem, the left side, typically, you're going to put all the digits in the numbers except for the last one. So since each of these numbers have 3 digits, the stem is going to have the first 2 digits on the left, and you're going to go in order. So for example, the lowest value we have is 152. And the highest value looks like 189. So our stem will first be 15. And we're going to go all the way up to 18, making sure not to skip any of the whole numbers in between. So 15, 16, 17, 18. So it's just those 4. Then need to actually make it this tall. Then what you do is you put the last digit of each number to the right of it, going from lowest to highest. So for example, the lowest value is 152, and cross that off, and I'm just going to put the 2 to represent that. And when I do this, I'm going to make a key. Always make a key when you have these so that readers know what your units and how to read your graph is easily. So if I put 1, 5, then I put that /2, that's going to stand for 152 centimeters. But anything like that, that's enough. Now I'll go in increasing order. So the next 2 highest are 55s. So 155. So I'm just going to put 2 5s in a row like this. Leave a little space. Don't put any commas or anything. Just leave a little space. Make sure it's all like uniform. Then I go 158. I put the 8 to represent 158. Nothing in the 150s anymore, so I go to the 160s. at low, I have 3 160s. So for 160, I put a 0, and I put 3 zeros, just like that, because that's the lowest a value could be that starts with 1/6. And the next highest value would be 163. So that would be a 3. Then I have 2 169s. So I put a 9 and a 9. Okay, now I move on to the 170s. The lowest 170 I have is 172. So I just put a 2 in the next row. If I have 3 173s. So I'm going to put 3 3s. Again, keep them equally spaced so it's nice and organized. And then I have a 175. So no more 170s, and the last one is actually the 189. That'll be the biggest one. That would be there. And that's it. That's all there is to it. The STEMplot is pretty simple. Now what I'm going to do is make a back-to-back STEMplot with this same data. So this actually is really simple, especially once you've already made one STEMplot of the data. I'm going to make basically a double-sided stem. I'm still going to include the same values in the middle because I know that's what the values are going to go from. So I'm going to be 15, 16, 17, 18. And then on one side of the stem, I'm going to have one group. So I'm going to put the females on the left. And on the other side, on the right side, I'm going to have the males. And so same basic idea, except I can just do one group at a time. And the thing is, when I'm doing the females, I go from the right to the left. So kind of going backwards. So for example, I would do the 152 first. So I would put a 2 like this. Then I would do the 155s. Now I'll put them to the left. And then followed by the 158. Now I look at the 160s for the females. I have 3 160s. I'm going to put 3 zeros. 1, 2, 3. And I have a 163. And I have a 169. I put a big line here to make sure they don't interfere. Okay, now the last one I have, or the last two I have for females are the 172 and the 173. So 172 first, like that, and the 173 like this. Now I do the males just like I normally would in the first STEMplot, going from left to right. So the lowest value I have is 169. So I'll put a 9 here. I have 2 173s. So 3, 3. And then 175. And the last one, 189. Now, there's not much data, I just happen to have a small class this past year, but one of the advantages of having a back-to-back STEMplots is you can see how the data within the data, compares. As we know, males tend to be on average taller than females. So we can see that the values for the males tended to be grouped higher than the values for the females. And that makes sense. Now, even with this, again, I only had about less than 20 values. If you had more with 30, it would probably be more clear on the patterns of each group. Now, a couple tips to remember when we're making a STEMplot. It's really not a good idea to make STEMplots for big data sets. When you have big data sets, it's going to kind of become tedious, and sometimes the values and the shapes don't really stand out. It's going to not really tell you much, or it's gonna be very hard to tell you much. So I usually try to, not do them for anything above 30 or 40 values. It really just depends, but bigger data sets, we're gonna learn about how we can use histograms for that. Now, there's not a magic number for how many stems to use, but usually 5 is a good minimum. Too many or too few doesn't let you see, the distribution shape. So you can see, like, since we had a small set of data and we only use 4 stems, it was kind of like hard to really see what was going on. But again, we didn't have that many sets of data or had that many values in our data set. Now, if you want to split stems, I'm going to do an example later on. So you can split a stem so that you could have like 1, 5, 1, 5, 1, 6, 1, 6, and so forth. And then you would put the first 5 digits, 0 through 4. So the first 1, 5. Let me actually just show you what I mean. If I split my stem something like this, this first one would only hold the digits 0, 1, 2, 3, 0, 1, 2, 3, 4. And this next one will hold 5, 6, 7, 8, 9. So we can break the groups up into, into subgroups within each stem, so you can better see how the data is distributed. So when you split them, just make sure they each have an equal number of stems. Now, you could do it, like this, or you could actually do it the other way. You could go like, you could do 10 15s and only showing, 2 digits, 0, 1, 2, 3, 4, 5, and so forth on each digit, on each stem. Now, depending on the type of data you're dealing with, determine if you want to round. Sometimes rounding to some significant digit makes sense. So in this example, I had my students round their heights to the nearest centimeter, even though 1 inch is 2.54 centimeters, and some of them got decimals. But it just made more sense to keep it to the nearest centimeter. So keep that in mind when you're dealing with data, because it's not going to be the same for every distribution.